Welcome to Complexity Made Simple. My name is Paul Allen, and the subject of today's video newsletter, well, we're going to take a look at something that's becoming really important in the world of big data, but a little bit technical, but so important if you are trying to take historically collected data and to understand something from your data sets. So we're going to take a look at something called confounded data. So this is, as I say, it's a little bit technical, but this is super important. We're getting so much information now about big data. We're going to take huge data sets from computers that have collected everything from a production facility, and somehow we're going to run it through some magic software, and we're going to learn something that we couldn't learn by normal means. But if your data is confounded, data will lie to you. You will not find the truth out if you analyze confounded data. So we're going to take a look at a little example, and I'm going to show you what confounding actually means. Okay, so what we're going to have, typically you're going to have an historical data set. Now I'm only going to put two data sets up there. So you know, you got input A, input B, and of course what you're going to have is maybe something like temperature, something like pressure. And what you're going to have, of course, is you're going to have some random values for temperature. Yeah, so you will have collected these random values. So maybe the temperature, I don't know, I'm just going to make some numbers up. So 46, whoops, 47, 49. Okay, so we've got some random values, and of course I'm just drawing a small data set, but this could be hundreds or thousands of rows long. This could have many more than two inputs. You might have 6, 7, 8, 9, 10. You've just collected every readable measure from your manufacturing process, and you've just put it into a big computer in the hope of creating big data and learning something. So we've got the temperature, which is being randomly moved around. Then we've got the pressure, which is also randomly being moved around. So I'm just going to put some random numbers in here, as if a technician has been testing and learning, etc. Okay. And then what we've got, of course, is an output, something that we're interested in. And again, this might be more than one. This might be more than one output. We're going to suggest that this is the hardness of some product that you've made. And again, of course, we're going to measure this, and this is going to just be historical data. So we will have collected the production settings, then we will collect the hardness values. So and we'll have, essentially now we have a data set, which of course we can then analyze. So we've got this data set, and there's this idea now that we can analyze temperature versus hardness, and we'll learn something. Pressure versus hardness, and we'll learn something, and we'll then be able to move those two dials and hit a particular target. But the way I've drawn these two variables, they are highly confounded. And when you have confounding in your data set, you cannot see what's going on. You cannot see the truth. Okay, so what does that mean? Well, look, as we run down the table, temperature has been increasing. Yeah, so it's increasing in value as we run down the table. But also at the same time, look, as we've gone down the table, pressure is also increasing. In some ways, let's have a look in a slightly different pattern, hopefully. So maybe I'll change a few of these just to make it a little bit more like that. So if we take this out, we'll just make these, let's make these slightly different just to show you that they are different values. But that column is increasing as that column is increasing. These two columns now are confounded. So what's going to happen now, and of course the hardness value is increasing. So if you look at what's going on, the hardness, look, as we ran down the table, the hardness has increased by approximately 7 points. Okay. So if I did an analysis on this data, what you would see is this. You would see this is highly correlated to hardness, and you would think it's moving the result by 7 points. You would look at the relationship between the pressure and the hardness, and you would think that the pressure is moving the result by 7 points. But you can't double count that effect. One of them is moving the 7 points, or maybe both of them is having an impact. There's 3 points from one and 4 points from another. But you can never know how much is coming from each variable. Maybe it's all coming from this one, maybe it's all coming from this one. And that's because these two variables are confounded. They've been changed in a similar pattern, and then what you do is you double count the effect. Okay, now I've got a data set, so I've got some data sets that have been created in a similar way on my computer. So we're going to have a look at this data, look on Excel, and then what we're going to do is we're going to have a look, can I see correlation between this one and this one? Can I see correlation between this one and this one? But actually, how much correlation is there between these two? Because if these two are linked, they are confounded, and the knowledge we are looking at is useless. It is lies. We are double counting the effect, because what we'll think is if I wind on this and I wind on this, I'll be able to move the hardness by 14 points. Of course, that's not true. You can't double count the effect. So let's take a look at some data on the computer. We'll do a little bit of analysis and we'll see what we see in the way of confounded data. Let's take a look. Okay, so here we are. We've again got temperature and pressure, and I've got two versions of the data. I've got one version of the data which is over on the right hand side here, and the way that I've organized the data, I've put the data in order, so you can see temperature starting low and then going high. You can see pressure starting low and going high, etc. So I've ordered the data. But of course, that probably isn't how you get the data given to you. What you'll have, because the data has been randomly collected, you'll see the pattern over on the left hand side, which is just random data collected. So when you look at this, 43 on the temperature, 62 on the pressure, and 102 on the hardness, then the next one goes 58.71 and the next one goes 69.85. You actually can't see the fact that temperature and pressure are linked together. They are confounded. They are moving from low to high at the same time, and we are double counting the effect. So first of all, let's just do some basic regression. And here we've got, look, pressure versus hardness. So if you look at this scatter plot here, I've got pressure versus hardness. I've got an R squared, look, of 0.8. That's a really good R squared. That's telling me that 80% of the effect in the hardness is because of the change in the pressure. And I've got a nice prediction equation to go with it. But then if I do the same thing with temperature versus hardness, so temperature versus hardness, look, I've got an R squared now of 0.94, which is a really strong relationship between temperature and hardness. Now, if you look at these two graphs, you can see that they are moving. They are moving. Let's just get a pen to run here. they are moving 30 points up the scale. So this high to low here, when I move temperature, I'm getting a 30-point shift for temperature to hardness, but I'm also getting a 30-point shift for pressure to hardness. Yeah, so this is going up 30 points as well. But what I'm doing, I'm double counting the effect. The whole effect is 30 points. Some of it comes from pressure, some of it comes from hardness. But because what we've done is we've mixed the two variables together, we cannot pull the effects apart. Now look, the last diagram that I've done, I've actually done a regression analysis between temperature and pressure, and you can see, look, I've got an R squared of 0.9, which means that temperature and pressure are linked together. They've been changed in a similar pattern, and therefore the information that I have in front of me is useless. It isn't telling me the truth, and actually using this data set, I can never know the truth. I'll never be able to separate the effects out. The maths is so mixed up, it cannot be analysed by even the most powerful computers. Confounding is a really big problem. Now what I've done, I've put the data into my DOE software, and I'm going to try to analyze it. Now my DOE software is going to tell me how much confounding I've got, so it's going to explain that to me. So if I go analyze design, multiple response regression, I get a little regression table here. I'll just blow this up so we can see it a little bit better. So if we blow that up nicely, so what you can see now is in the coefficient column, this is the equation that tells me what temperature and pressure is doing. So you can see that for each unit of temperature, I get an increase of 15.5 on the hardness. For each unit of pressure, I get an increase of minus 3.6 on the hardness. So you can see that I've got the regression equation there. But these coefficients are double counting what's going on. But if you look at the tolerance column, what's the tolerance telling me? It's telling me how clean is that 15-point shift in the coefficient. And it's saying 0.09 on the tolerance, only 9% is clean. In other words, 91% of the signal is coming from somewhere else. This data is not to be trusted, and that's what confounded data is like. It is not to be trusted, and therefore we have to get away from confounding and think about new data collection. Think about using a DOE. So what we really need to do with these data sets is we really need to collect properly designed experimental data. What we don't want to do is collect historical data. The patterns in historical data will often lie. And before we just take a look at what a properly designed experiment would look like, let's just consider one other problem with this confounding pattern. The way I've drawn these, of course, is that this increases and this increases, and that we get this 7-point shift. Just imagine though, it's the other way. Imagine that this increases, but this particular variable is decreasing, so it's the other way around. Imagine that this has an effect, it genuinely has an effect, let's say of 8 points on the result. And that this one genuinely has an effect, but let's say it has an effect by 6 points. Well, if I turn this up whilst I'm turning this down, and then I try to analyse what's going on this end, what will I see? Well, actually, I'll see almost nothing. Neither of these will look as if they do anything to the output. So I'll get the opposite problem. Now this is important, But when I do the analysis, I see no importance at all. I see no R squared. I see low R squareds. And I'm just going to think, oh, these two don't do anything. You see how confounded data will just give you absolutely terrible information. So what should you do? Well, what you should do is you should test these two variables in a test that you have designed, not one that's been randomly collected, not one where the dials have simply been twiddled around in the hope of learning something. What you should do is a balanced orthogonal pattern, and a balanced orthogonal pattern would look like this. We would test at the low value for temperature. We would go down and we would test the high value, what's that, 52 there, for the temperature. So we'll do a couple of tests at the high. There's the first part of the test. But whilst I'm doing that, I'm going to be testing pressure in a balanced way against it. So now what we do is we go low on the pressure, would be 102. High on the pressure would be 110. So you can see, look, it's a different pattern. Low, low, high, high. And we've alternated here, low, high, low, high. That is balanced. Why does balance work? Because we've done an equal number of lows and highs against these two values, an equal number of lows and highs against these two values. What does that do? It cancels out the effect on blinding us to what temperature does. So now I will see clean and clear what temperature does, clean and clear what pressure does. If you are someone that does AI, you're doing automatic learning, you're doing machine learning, or you're doing big data analysis, if you don't understand confounding, you don't understand how to get a balanced orthogonal pattern, you won't learn what's going on. Your software won't get the best analysis. Your software won't get the best results. The best way to learn how a system works is always to use what's known as a truth table. In computer science, this pattern is known as a truth table. That's why we use them. Avoid confounded data, avoid historical data and big data, do DOEs, learn fast and make more money.